Here the question number 83, which one is the correct? Here, if you look at all the option, it is given the one-dimensional linear harmonic oscillator equation. To solve this problem, what we have to do, we need to write the Lagrangian for the linear harmonic oscillator. Then we can do the equation of motion. Finally, we will arrive the given four equation. One of the equation we will arrive. That is the thing we are going to do it right now.
So, in this question, they have asked about the one-dimensional linear harmonic oscillator, that equation of motion, how it will be looking like that. For that, we need to write the Hamiltonian of the, I think Lagrangian is enough. Suppose take this is a linear harmonic oscillator. It is fixed here. The mass is m is attached to the spring or spring constant k. This is a mass. This is spring constant k. This is a frictionless surface. Suppose take this is a surface. This surface is frictionless. It is touching with the frictionless surface, the mass m. What would happen? Suppose if you are giving the force this direction, the applied force is on this direction. This is F applied. There is some displacement. If you are taking this as x equal to 0, then definitely the rigid body move up to this distance, that you can call it is x or x minus x0. Suppose if you are taking this from here to the distance is x, just if you are pulling this one, it will come up to here. So the displacement, maybe you if you are concentrating the center, you can just put the diagram here. So if I am pulling this mass m up to here, the center of the mass m, that we can call x from the fixed rigid position. So the distance is x. The restoring force, what it will do, it will act on the opposite direction. This is applied force in this direction. The restoring force is responsible to restore the position of the mass m to the original value. If you are releasing, what it will do, the spring will expand the restoring force acting on the opposite direction. Then the mass will come here. Then it won't stop because it's a frictional surface. So it is smooth. The spring constant, what it will do, it will get compressed because of the inertia of the mass. Then it will still in motion, so it will be compressed this spring. So it slowly decreasing its acceleration. What it will do, the mass will come up to here. Then after that, this restoring force will act in the opposite direction. That restoring force, then the mass will go here. Then it will execute the simple harmonic motion. So here one thing we have to understand, the force is proportional to the Ex, or the force is equal to minus k time the x. Proportional, if you are removing the proportionality, you got to add the constant. That constant we can call it the spring constant. We know the force, when the force will be there, means there is a negative gradient of the potential. That is a classical expression for the force. If the negative gradient of the potential will be there, then definitely the force will be there. Here we are calling this is a restoring force. In general, this law you can call it's a Hooke's law. This is a Hooke's law. So for finding the potential energy, kinetic energy anyway it will be simple. For finding the potential energy from the force, we are using the classical expression. The force is equal to the negative gradient of the potential, that would be equal to minus kx. If you are removing both side k, then the dou u equal to minus k plus k dou x. Here the only one variable x. Here the potential energy, you can change dx. Instead of partial derivative, you can change the total derivative. If you are taking the du here, if you are taking the integration on both side, it will give the potential energy equal to of k x square by 2. If you are taking this integration, it will be x square by 2. So this is the potential energy for the simple harmonic oscillator. What is the kinetic energy? It will be simple. The kinetic energy T, in general you can call the using the symbol T, that will be equal to of m, the velocity square, you can call small v, the velocity square. This is the kinetic energy of the particle. At a extreme point, suppose if you are pulling this mass m, at a extreme point there is a displacement, but velocity goes to 0. Kinetic energy 0, purely it's a potential energy. When x is equal to x naught, that means maybe if you are taking this as a reference point or the origin, the potential energy is completely 0. X goes to 0, its potential energy is 0. Then purely it's kinetic. At the center, it's purely kinetic. There's a mass originate located. When it reaches that position, the velocity will be maximum. So you can take the point, reference point x equal to 0. X equal to 0 means potential energy is 0, purely kinetic. Then again, if it is moved to the left hand side extreme point, the potential energy will be maximum, kinetic energy 0. In between these 3 points, 2 extremum maximum potential energy, then 1 point is at center. These 3 points, the purely potential in these 2 points, purely kinetic at the center. In between any 2 points, except those 3 points, it's a partial potential, partial kinetic. But net energy is conserved. The system will obey the energy conservation law. Now, how we need to find the equation of motion means, just we have to write the Lagrangian. Lagrangian from the classical mechanics, we know it's a kinetic energy minus potential energy. This is the Lagrangian of the system. So the Lagrangian equal to kinetic energy is of m v square minus potential energy is of m x square. Already we know the kinetic energy, potential energy. So the velocity we know from the definition, it's a rate of change of position dx by dt, or you can call any time derivative by putting x dot. So the v square you can replace at x dot square. X dot square first of m x square. This is the Lagrangian. Now once if you have the Lagrangian, then it will be simple. We need to do the equation of motion. Therefore, the equation of motion EOM, that would be equal to, from the Lagrangian, that will be d by dt of the dou L by, here only one dimension, so x is a variable, so dou L by dou x dot, this is generalized momentum, minus dou L by dou x, that would be equal to 0. This is the equation of motion for the linear harmonic oscillator. So d by dt of, first we need to find the partial dou L by dou x dot. If you are taking the derivative dou L by dou x dot, here x dot will be there, here there is no x dot, this term goes to 0. If you are taking this derivative dou L by dou x dot, 2x dot, 2 will get cancelled, we will have m x dot here, minus dou L by dou x. Dou L by dou x, there is no x in the first term, this term goes to 0. If you are taking the derivative the second term, minus 2x, so 2 will get cancelled, so minus m x equal to 0. Here m is constant in the 2 term, even the mass of the body is constant, so derivative nothing to do with the mass, so it will act only the x dot. Already dx by dt, if it is acting on the dx by dt, d square x by dt square, so that you can express by 2 dot. That means second derivative of the second order differential equation of the position vector with respect to time, mx double dot. So x we are taking commonly out, minus and minus plus, x is equal to 0. Or if you are pushing that side x, that will be 0 by d0, so x double dot. Here one thing, actually here it's not of m x square, here kinetic and potential energy of k x square, that mistake I had done, of k. So here k, you need to change wherever the potential energy, so here you can't take it, the m is constant, so you can keep it inside. So here what we need to, so if it will operate only in the x, so it will give x double dot minus into minus plus, so kx equal to 0. This would be the equation of motion for the one dimensional simple harmonic oscillator. So this is the final expression. Here we did one mistake, that instead of k we put a m, that's why the confusion. So finally we will arrive this equations. If you have this equation, then that would be the right answer for the given question.
From the above discussion, we got the answer that would be mx double dot plus kx equal to 0. So this would be the right answer.